All right, so part two of this sequence uh, video stuff. Um, so remember we were talking about this idea of a sequence with a list of numbers, right, that are created by some sort of pattern. Okay, so what we want to do is what if this pattern were to keep going, right? So it's all about the calculus stuff now. So now what we need is the limit of a sequence. So before you had a lot of different types of limits when you're talking about functions, right? They can approach this number or it could go off to infinity or negative infinity. So at least here we're only going to go off to infinity, right? And so it's only one thing you got to worry about. So but what we're talking about is, let's talk about the limit as n goes off to infinity of this nth term. And let's say this turns out to be L. Okay, then basically what does this mean, right? If this actually converts to be a number, I mean, there's a whole epsilon delta version of this limit of a sequence idea, just like it was for functions, real value functions. But the basic gist of it is, if this limit turns out to be L, then think of it as the terms. Oh my god! Then the terms of a sub n, right, that sequence approach L as n goes off to infinity, right? Or in other words, think of it, there's a list of numbers here, right? So you have this list of numbers, and if the list of numbers is getting closer and closer to some number, then that limit is L, right? But if the list of numbers, that sequence, is not getting closer, then the limit doesn't converge to a number. Okay, so think of it. It's very similar to functions. It's just that remember, with instead of functions being nice, smooth, continuous, or it doesn't have to be smooth, but nice, continuous objects, we're talking about what's happening at the dots, right? At the corresponding integer values, right? Positive integer values, right? So, for example, I mean, if you saw something like, let's just quickly look at, if I wanted to find the limit as, let's say, x goes to infinity, right, of something like, I don't know, 4x minus 5, right? So what we're talking about here is a whole function, right? So it's a nice line, 5, and then it's going to 4, right? So we're talking about this line here. Now, obviously, this is going to diverge, right? Because as x goes off to infinity, this is going to go off to infinity, right? But what I'm talking about is the limit as n goes off to infinity of this 4n minus 5, right? It's the same thing. It's just that instead of this continuous line, you now are talking about what's happening at maybe, well, I guess 1 would be down here, then 2, right? So again, it's now we're talking about the dots, right? So this is referring to what's happening at only the integer values, right? So imagine what's happening at only at the integer values. But the same basic thing applies, is as n goes off to infinity, right? I mean, you could visualize this sequence, right? If I started at 1, right, what would that be? Negative 1, and then it's going up by 4, right? So then it would be 3, then 7, then 11, right? But obviously, well, hopefully, obviously, right? If the sequence were to keep going, the terms are just getting bigger and bigger and bigger and bigger. So this would indeed also diverge or go off to infinity as well. Okay, so a lot of times that's what's going to be helpful is, if remember, these are only dots, right? It's a series of dots here, right? So it's only what's happening at discrete dots. I mean, they're not continuous, right? So sometimes it's helpful to think about the analogous real valued continuous function, because then things like L'Hopital's rule, right, which is going to obviously come in if we're talking about limits, is going to apply. So you can kind of jump to L'Hopital's rule when you're doing these things. Like obviously that wouldn't apply here, right? But what I'm saying is, well, even if it doesn't even apply here, but what I'm saying is a lot of times you can jump right to it in your brain and think of it as, hey, instead of a sequence, let's look at the corresponding function, use L'Hopital's rule, and then go back to the sequence. But you can just make it flow. Okay, hold on, that'll make sense in a minute. Okay, but one of the biggest things that we need to get out of here, and I think this is probably the biggest discussion, is especially it's going to help moving forward, right? Because moving forward, we're not only going to talk about these things going off to infinity, but then also start adding things up, which we'll get to in a minute. Well, not today, but soon. But you want to be able to get used to being able to look at a function and classify it, right? And not only type of function, but the rate at which it's going, right? How fast is it going? And then I think you've done enough of this. We've all kind of put this together in your head maybe already, or at least started to. So let's talk about types of functions. And more importantly, and the rates of these things, you know, n going off to infinity, right? So remember, we're talking about is n going off to infinity here, right? So things like constant functions, obviously they're not changing at all. Things like polynomials, I'll give you some examples in a minute. So polynomials, roots, radicals, right? Logs, exponentials, and then trig stuff, right? So these are different types of functions, and you want to be able to classify these things in terms of what are they doing as we go up to infinity? Are they going up to infinity? Are they not going up to infinity? And then more importantly, which one is going faster? And you want to be able to rank them, basically, right? I mean, obviously, a constant function not going anywhere. It's constant, like being 8 or 10 or 12, right? If your sequence is just consider a sequence of numbers, which is 8, 8, 8, 8, 8, 8, 8, or 10, 10, 10, 10, 10, 10, what, forever. Obviously, that's not going anywhere, right? So that's kind of boring. Also, trig stuff does some weird things, right? So we'll get to those in a minute. But those don't really go off to infinity, depending on what these definitely not, but trig maybe part of it at least, right? But let's talk about these, okay? The polynomial, the roots, radicals, logs, exponentials, okay? And we want to talk about the rate. So polynomials, like, what are we talking about? We're talking about like n or n squared or n cubed, right? You're talking, I mean, again, there may be some other stuff below it, right? But you're talking about n raised to powers. Now, usually those powers are nice in order to be a polynomial, right? These are, nice whole number powers, okay? And then roots and radicals would be like your square roots or cube roots, right? Or basically n raised to some fractional power, usually. And then logs would be, like you would have log base 10 or maybe the natural log, right? And then exponentials would be like 2 raised to the n, or maybe 1/3 raised to the n, or e to the n, right? So again, don't confuse these two. The base with a polynomial is the thing that's changing, but the power is set in stone. Whereas an exponential, it's the opposite. The base is what's set in stone, and the exponent is what's changing. Okay. All right. So think of this as, let's rank them. I want to go fast, and I guess slow, right? So of these, well, this is probably not one of those things. Pause it. Let's see if you can do that. Rank these. Like who use as n goes off to infinity, who would go off to infinity the fastest, right? Oh, I probably make sure you know what I'm saying. It's like this is not going to infinity. This may or may not be going to infinity depending on which one you're talking about. Well, actually none of them, but individually anyway. But a combination of them might. But if n's going off to infinity, these are going to get larger. 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 All these are going to go off to infinity. But what I'm more interested in right now is the rate in which they're going to go, right? So if you haven't done so already, pause it and see if you can put these in order, right? Slowest to fastest. Okay, so hopefully you see that the exponential is by far the fastest here. Okay, it's one of the very fastest ones. Turns out, basic function-wise, there's only one that's faster, which we haven't talked about yet, which we'll get there. But think exponential ridiculously fast, right? Then after that, you got your polynomial stuff, right? Then you got your roots and your radicals, and then the logs are really slow, right? So, I mean, graphically speaking, picture a log goes like this, and it's really slow, okay? A root and a radical kind of is the same thing, but not, it still has that concave downward feel to it, right? So it's slow, but it's way faster than a log, right? Then a polynomial, right? I mean, picture like a u squared or something like that, or a n squared, right? I mean, it's going to shoot up really fast, right? Like a parabola or any other power. But an exponential shoots up really fast, okay? So you want to be able to kind of visualize. A log keeps going up, but really slow. A root, a radical of some sort, right? Probably should put an n here, right? Still going upward, but it's slow. It slows it down than n, right? Now, a polynomial speeds it up, right? So something like n squared or something like that definitely speeds it up, but nowhere near as fast as an exponential, right? So an exponential is definitely going to be a lot higher. So keep those in mind. Now, as far as obviously a constant, that one's really dumb. It's not going to come up much because it doesn't change at all. But trig, one thing especially, think of sine n and cosine n, for example. Sine, remember, starts at 0 and it goes like this, and then it bounces, okay? But the thing is it bounces back and forth. So it's not going off to infinity, nor is it actually going to something either. It's literally just bouncing back and forth between -1 and 1, right? So this isn't going to, as it goes off to infinity, it's not going to converge at all. And the same thing with cosine. It would just, with cosine, you're talking about it starts up here, and then does that, right? But again, that's the point. Both of those are kind of stuck between -1 and 1, right? But they're not converging to anything either, right? If you go out far enough, it's not getting closer to a number. It's not shooting off to infinity either. So just keep that idea in mind, okay? So the basic sine and cosine trig stuff, remember, they are bounded, right? They're stuck, not getting any higher, not getting any lower, but they're not going towards anything either. And then especially here, when you see logs, roots, polynomials, exponentials, we got to be able to rank those. Okay? All right, so let's do it. So what I want to do is, well, just determine if sequence is given in term. This is just laziness on my part, but I don't think this is too mind-boggling because Trust really get tired of that phrase converge or diverge, because pretty much the whole chapter, well, the majority of the next chapter is all about this idea of converging or diverging, right? Converging meaning getting closer to a number, diverging meaning not getting closer to a number, right? So determine the sequence with given nth term converges or diverges, and then if it does converge, find its limit. Okay. I'm going to do a bunch of these, and again, we got to just play around with these things, right? And some of them you want to be able to look at and know what's going on without having to do a whole lot of work, right? So, like something like this. Again, I'm not going to lie to you. You should be able to look at this and not a whole lot of work, know what's happening, right? But again, it has that polynomial feel on the top, polynomial feel on the bottom, right? So really, you don't have to write it all out. I would imagine you probably just look at this and see what's going on. But what are we talking about? We're talking about the limit as n goes to infinity of this. Okay? So the top is definitely going off to infinity. The bottom is definitely going off to infinity. Now, technically, this is a sequence. So L'Hopital's rule does not apply because it's not a continuous function, right? If you don't have a continuous function, then derivatives don't make sense. However, this is what I was talking about earlier when I was saying you can kind of just jump to it, meaning what we're talking about is a sequence, right? This thing only works when n is 1 or 2 or 3 or 4. None of the stuff in between, right? None of the crazy decimals. So these aren't continuous things. But if I were to look at, in my head, the analogous real valued function x squared minus 3x over x plus 4, then L'Hopital's rule applies, right? And then you can switch it back, right? So you could jump to it, but do realize you are circumventing things and you're looking at the analogous continuous real value function and then coming back to the idea of a sequence, right? But you could use L'Hopital's rule in this if you wanted once you do that. So then the top would just be the 2n minus 3, and the bottom is obviously 1, and then the whole thing doesn't shoot off to infinity. But the ultimate point, when you see something like this, it kind of goes back to that ranking idea, right? So when you're talking about polynomials, right? When you're talking about polynomials, you're talking about n raised to the p. If you're talking about roots, you're talking about n raised to the p. But polynomials, your p is going to be bigger than 1, right? Like n to the 1, or n to the 2, or n to the 3. If you're talking about a root or radical, right? You're talking about a fractional power, right? So your p would be between 0 and 1 when you're talking about roots and radicals. And hopefully you realize the larger the p-value here, if you're in the polynomial world, the faster it's going to go, right? Makes sense? So when you see something like this, you say, oh, look, the degree of the top is larger than the bottom. So that obviously this infinity is going to be much larger than this, or going to this infinity is going to be faster than the bottom is going to infinity. So of course it's going to be infinity, right? I mean, by the same token, if I gave you the exact same problem, but switch it, so I guess it's not the same problem, but same functions. Again, you could look at this and say, hey, look, the bottom's going to go a lot faster than the top, so this would indeed go to 0. Done. I don't need a whole lot of work here. But that's the idea when you get used to that, right? So let me give you a different one. So let's say I gave you something like 5 cubed root of n minus 1 over the 4 n cubed plus 1. And it might even be worth, let's do this. Let's do 3 of these all at the same time so you see what I'm talking about. So what if I gave you the same thing, but now it was 4n cubed plus 1 over 5 cubed root of n minus 1, right? Or let's say I gave you 4 cubed root of n plus 1 over 5 cubed root of n minus 1. So slightly different ones here, right? But so this is like a cube. It's a cube root, and the bottom is, so this is like a root and a radical, right? This is a polynomial. The polynomial is going to take over, right? I mean, so again, technically this is infinity over infinity, but this infinity is going to take over, and that's why it's going to go to 0. Done. Here, again, this is infinity, but this polynomial is going to take over. That's why it's going to go off to infinity. Done. Here, these are infinity over infinity, but now they're both roughly the same. So since they're roughly the same, all that really matters is that 4/5 out front. right? And that's the point. Without going through the whole, technically you have to transform this to a real valued function, and then you can use L'Hopital's rule on top and bottom, right? And the same thing with all of these. You could, think of the analogous real valued function, use L'Hopital's rule, then come back to the idea of sequence. But the point is you get used to this idea of how fast things are going, and you just look at it. Bottom's going to go faster, 0. Top's going to go faster, infinity. Going at about the same rate, they're going to collide with that leading coefficient out front. And there you go. Makes things a lot faster. Okay, so I guess that was 5. Let's try this. Let's say I gave you something like, I don't know, n to the 10th, and the bottom was e to the n, right? And even the same thing, let's do it the other way. So let's say I gave you e to the n over n to the 10th. And then let's say I gave you something like n raised to some power p, let's call it an arbitrary p here, over e to the n. Right, so hold on, let me talk about these. So this is a polynomial, right? This definitely has a polynomial feel to it, and this is an exponential feel to it. Now this polynomial is going to go up really fast because it has a power of 10. But the question is would that be enough to counteract the exponential? And that's no. The point here is this polynomial, yes, it's a big power, but think about that. Again, you could go to the corresponding, so first off, we are talking about infinity over infinity, right? Going off to infinity, this is going to get larger, this is going to get larger. But think about the corresponding real value function. You could use L'Hopital's rule. You'd have to do it a bunch of times, but eventually, if you took enough derivatives of this, it's going to go away. No matter how many derivatives I take at the bottom, it's never going to go away, right? So that's the point, is this exponential is growing way faster, so that one's going to take over, and that's what's going to cause this thing to converge to 0, right? The exact opposite, same thing here. This is infinity over infinity, but this is still going to go faster, right? Since it goes faster, then it's going to diverge, right? It's going to go up to infinity, right? Or in other words, just diverge. So I guess that's the question I'm asking here is it possible to create a polynomial? Like, how big would this p have to be able to counteract this? Okay? And hopefully you can see it doesn't matter. This is always going to diverge for any p. I mean, even if p was huge, like 1,000,000, right? If p were like 1,000,000, yes, this would be incredibly fast. Like n raised to the 1,000,000th power would be huge. Now, for small values of n, this would be nothing compared to n to infinity, right? I'm pretty sure like e squared, or e to the 4th, or e to the 5th, or e to the 6th, or e to the 7th. That's nothing compared to 1 to the million, or well, not 1, but 2 to the million, 3 to a million, 4 to a million. That's going to be enormous. But eventually, you're going to get out far enough, right? You're going to get out far enough that having that exponential so big, because remember, we're going up to infinity, that it will counteract and still blow away this polynomial no matter how big this is, right? It may take a while, depending on, and p is huge, it may take a while for this to get there, but eventually, once I reach that cutoff point, it's going to blow it out of the water, right? Because, one way you can see this, again, if you look at the corresponding real value function, even if this were 1,000,000, you can keep taking enough derivatives. You'd have to take a lot of them, but eventually it's going to go away. This will never, ever go away, no matter how many derivatives I take, right? And so that's why it's going to grow faster. Okay. All right, so what if I had some trig stuff floating around, though? All right, so now here's the thing. If you're going off to infinity, I probably should stress this. If you're talking about the limit as x goes off to infinity of sine x over x squared, right? If you think of it as, it's the normal infinity over infinity, so I look at the corresponding real value function and then do L'Hopital's rule, right? And then you say, this is cosine, the bottom is 2x. No, don't do that, right? Even if you look at the corresponding real value function here, that L'Hopital's rule does not apply, right? That makes sense? You guys with that notation, the L'Hopital's rule does not apply. Why? Because remember, L'Hopital's rule needs to be infinity over 0 over 0, right? The bottom is obviously going to infinity, but the top is not going to infinity, right? Remember, it's bounded, right? Yes, it is bounded, but it's not approaching anything, right? So L'Hopital's rule doesn't even apply here. This is when you just have to use your brain on it, right? Think about this. The whole point is sine of n, no matter what you do, is always going to be trapped between -1 and 1. So the biggest the bottom could ever hope to be is 1, right? So yes, this is not a constant, but it's changing, but it's never going to be above 1. So if it's never going to be above 1, the bottom is going to take over, right? So if the bottom takes over, it would indeed go to 0, right? This is one of those you just got to think about it. Okay, even if you had something like, let me do a couple of these. What if I gave you sine n over the square root of n, or 11 here? What if I gave you cosine n over the natural log of n, right? Again, the top is stuck between -1 and 1. The bottom, yes, the square root slows it down, right? I mean, n squared speeds it up. This slows it down, but still, eventually, the square root of 100, the square root of 1,000, the square root of 1,000,000, the square root of 10 million. Yes, it's going to slow it down, but it's still going to get bigger. The top is changing, but it's never going to get bigger than 1, right? So it's always going to be some number that's less than 1 divided by some really, really big number. So this is still going to go to 0. The exact same things that happen here. Yeah, it's at different times. It's going to have different values, but again, the top is still stuck, never bigger than 1. The natural log really slows things down. It's really, incredibly slow compared to other things, but it's still going off to infinity. It's still getting larger, very slowly compared to most things, but it's still going to get larger. So something stuck that's never going to go above 1 divided by something still larger, the whole thing is still going to go to 0. Right? So the terms of the sequence would still go to 0. But that's the ultimate point here, is being able to look at these, understand the rates, and then be able to determine these limits without, a whole lot of work. Okay, last thing. Again, all this stuff is going to come up again later, but last thing, some of you may have seen this before, but go back to this. So rates of things, right? Logs are really slow. Roots they slow things down. Polynomials speed them up. Exponentials really speed them up. So the question is the exponential the fastest thing? It turns out there is something that's even faster. Okay, at least with one input, you'll see. There's this thing called a factorial, right? I don't know if you guys ever seen this notation before, but basically what it is it's a number with an exclamation point, right? It's just more math laziness and just came up with this new notation. I guess it's all made up in the beginning at some point. But basically what it is, this n factorial, think of it as it's the product, or multiply, the product of all positive integers that are less than or equal to n, right? Or usually the way they say it is you start with the number that you're talking about and you multiply by the next integer below it. Then you multiply by the next integer below it, and the next integer below it, and you keep going, right? I mean, it's probably easier if you start with something like, I don't know, 8 factorial. What does 8 factorial mean? It means 8 times 7 times 6 times 5 times 4 times 3 times 2, and then technically times 1. But most of the time you don't need 1. It's not changing anything. But that's technically what it is. So you're going from 8 all the way down, and you're multiplying it up. And then you're going to get some ridiculously big number here, right? This in comparison to other operators. So whatever it is, you can throw it in the calculator. But one thing I do want to mention, so like 1 factorial is obviously 1. Then 2 factorial would be 2 times 1, which is 2, right? 3 factorial is 3 times 2 times 1, right, which is 6. Then 4 factorial is 4 times 3 times 2 times 1, which is 12 times 2 is 24 times 1 is 24. Or one thing you can notice when you put them all in order, when you do the next one here, like 5 factorial, yes, it's 5 times 4 times 3 times 2 times 1. But notice when you write it 4 times 3 times 2 times 1, if you're doing them in lists like this, you don't need to do all that because basically you already have the previous one. So 5 factorial is going to be the previous one times another 5, right? And that's kind of what we're talking about now because it has that sequence feel to it, right? So when you take the 24 and then multiply by the 5, that's going to give you the 120, right? 5 times 4 is 20, carry the 2, 5 times 2 is 10, plus the 2, 12, so 120. So my point here is 6 factorial, without doing all the way out, is going to be the same as 120, the 5 factorial, times the next 6, or 720, right? And you can keep going, okay? Again, do you have to memorize those numbers? No, but it might help to see that, because look, 1, 2, 6, 24, 120, 720, 1, 2, 3, 4, 5, 6. Like, imagine a sequence of numbers. If you're only on the 6th one, I'm all the way up in the 700s already, right? And it's growing really fast, because then 7 would be 7 times that. 8 would be 8 times that. 9 would be 9 times that. Whoa, it's growing really fast, right? So factorial is very fast, okay? Couple things with the notation on this, though. When you see something like a factorial, make sure you realize what you're talking about is you're starting with that number, then you're going to multiply by the number right below it, which would be n minus 1, then the number right below that, which would be n minus 2, then the number right before that, which would be n minus 3, blah, 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 all the way down to the 5 times 4 times 3 times 2. And then the times 1 is up to you, right? But just getting used to that idea of, because we're going to be using this a lot, is arbitrary spot, and then you multiply by that arbitrary spot minus 1, and then 2 lower than that, and then 3 lower than that, right? So I mean, usually you would just do it, but something, for example, what I mean by that is like 23 factorial. You would start at 23, then you would multiply by 1 less than that, which is the 22. Then 2 less than where I started, which is 21. Then 3 less than where I started, which is 20. Blah blah blah, all the way down to 5 times 4 times 3 times 2 times 1. Right? And sometimes it's just helpful to use that notation. Okay. A couple other things. It's mostly just getting used to the notation here as well. But 0 factorial, well, most people when they see 0 factorial, they think, well, duh, that's just 0. It is not 0. 0 factorial is actually, it turns out to be 1. Why? Because it needs to be, not because it makes sense. Right? This would be analogous to, like, I don't know if you remember, anything raised to 0 power is 1. Why is anything raised to 0 power 1? Because it has to be. Otherwise, the exponential, all the other rules for exponents fall apart, right? I mean, because think about, like, 3 to the 4th. What does this mean? It means you take 3 and you multiply by itself 4 times, right? So if I had 3 to the 0, this is saying take 3 and multiply by itself 0 times. Or I'm using 4 3s here, right? So this says I should use how many 0 or how many 3s? You shouldn't use any of them. So by the normal exponential rules, this literally should be nothing. You're not doing anything, right? You're not using anything. It shouldn't even do anything. It should be just a blank, right? But this needs to be 1 for all the other rules to work. It's the same thing. Like, what does 0 factorial mean? You're taking all the positive integers that are less than or equal to n. There aren't any, right? There are none, right? So there are no positive integers that are less than or equal to 0. There are nothing. So 0 factorial, by that normal definition, you should do nothing, just like this. There should be nothing here at all. But this needs to be 1. This needs to be 1 in order for all the other things that we're going to use it for to work properly. So it's kind of like an extra definition, a bonus, if you will, right? So this is what it means, but then also keep in mind that 0 factorial is 1. Okay? So we're going to need that. Okay. Other things. Kind of like exponents in the aspect of do not confuse these two things. Right? See the difference? I mean, like, it's kind of the same thing if I gave you 2x cubed or if I gave you 2x cubed. Those are saying two different things, right? This cube is acting only on the x, whereas here it's acting on the whole thing, right? It's the same idea with factorial. This factorial is acting only on the n. This factorial is acting on the whole thing. So make sure you see the difference. So what this is saying is n factorial, which is n times n minus 1 times n minus 2, blah, 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 all the way down to 2 times 1. But then there's a 2 out front multiplied by the whole thing, right? Whereas here, this is saying you're starting with 2n, right? It's the same start, but now you're taking that whole number, 2n minus 1, and subtracting 1. That whole number is subtracting 2, blah, blah, blah. Then eventually, because this number is going to be way bigger than n, right? It's going to be twice as big as n. So eventually, you're going to get down to just n, then n minus 1, then n minus 2, then all the way down to 3 times 2 times 1, right? I mean, what might help here, check this out. Maybe look at a quick example before we go to use this. Like if I gave you, I don't know, 2 times 5 factorial versus 2 times 5 all being factorial. Right? This means 2 times the 2, basically the 2 is just coming along for the ride, it's just sitting there doing nothing. But then the 5 factorial is the 5 times 4 times 3 times 2, right? But this 2 times 5 is really 10, then 9, then 8, then 7, then 6, then 5, 4, 3, 2, right? But that's what I'm saying. See, when you double 5, right, you're starting at the number that's double it. So eventually you're going to go down blah, 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 until I get to that number, the original ones. You see the 5, 4, 3, 2 is still in there. And then you're going to have the other half of that big number, 10 in this case, right? So do watch out for that. Okay. And then lastly, this is going to come up a lot over and over and over again, right? So make sure that you can simplify these things, okay? This is used a lot in probability. We're not going to mess with the probability stuff, but it will come up in our sequences and series that we get to in them later. But when you see something like 8 factorial over 10 factorial, okay, so what does this mean? You want to get in the habit of not having to write it all out because you're going to be here for a while, right? But what does 8 factorial mean? It means 8 times 7 times 6 times 5 times 4 times 3 times 2. And then the bottom would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, right? So you could throw this in the calculator, it's a huge number. Throw this in the calculator, even bigger number, and then divide. But notice what's going to happen. The 8, the 7, the 6, the 5, the 4, the 3, the 2 are all going to go away, so you're left with just 1 over 90. done, right? Because the only thing left is 10 times 9. And that's the point, is you want to be able to get in the habit of, when you see something like, let's say I gave you 9 factorial or 6 factorial, you can visualize in your head, hopefully, hey, what does 9 factorial mean? It's 9 times all the integers below it. But eventually, 9, 8, 7, 6, 5, 4, 3, 2. And the bottom is at 6, 5, 4, 3, 2, right? So that 6 factorial is going to cancel, or you can even write it as 9 times 8 times 7. Then once I get to 6, then think of the 6 all the way down, the bottom of 6 all the way down, those are going to cancel. So you're really only left with 9 times 8 times 7, which, whatever that is, you can figure that out. But at least that's the point. The 6 factorials cancel, right? All right, so let's say I gave you arbitrary one, right? Let's say I gave you n plus 2 factorial, and this is going to come up a lot later. Let's say I gave you something like n plus 2 factorial over n minus 1 factorial, okay? So something like this, you think of as, okay, if I have a number and add 2 to it, and I had a number and subtract 1 to it, this n plus 2 is going to be higher than the n minus 1, right? So let's start with the higher one, right? Just like here, you could have started with the 10, and then 10, 9, and then realize, oh, eventually I get to the 8 factorial, and then all that cancels. We'll start with the large one here. So think of, I'm going to start with n plus 2. Go with the one right before that, which would be the n plus 1. Then the one right before that would be n. Then the one right before that would be n minus 1. But now you've reached the other one. So that's the one you could stop at. And then say those n minus 1 factorials are going to go away. And so you're just left with the n plus 2, the n plus 1, and the n. Which you could multiply out if you wanted, but that's up to you. That makes sense? I mean, that's the idea. So just pick the larger one and just keep writing them all out till you get to the other one, and then you can cancel them off, and then that'll leave you with whatever's left there. Okay? So that's the idea. And then also, I guess I should say this, truly, hold on. Last thing. Let's just say I wanted to find each, well, I guess I should say find if each sequence converges or diverges, right? So if I gave you something like n squared over n factorial. Again, say to yourself, okay, obviously the top's going to go to infinity and the bottom's going to go to infinity, right? But what's going faster, a polynomial or a factorial? Basically, the factorial is the fastest thing we've got, at least in a closed format. So in that list that we created, in your list of, slow to fast, right? Logs, roots, polynomials, exponentials. In here should be your factorials, right? It's even faster than an exponential, right? You can play around with the numbers to see that, right? But that's the point, is here, this would definitely take over, right? So this one's going to take over. That's why it would definitely go to 0. Okay. One thing, for right now, you're just going to have to trust me on it. We can explain this why later. But what if I gave you something like e to the n over n factorial? Okay. Now, both of these are ridiculously fast, okay? Now, the problem with what we were doing earlier, like if you go back to all those other limits we were doing, like these or even these, all of these, you could come up with a corresponding, nice, analogous, real value function and use L'Hopital's rule and do it. Or just use your brain and think about it, right? But the problem here is there is no nice one, right? Because n factorial, by the definition of factorial, only works at the integers. There is no corresponding, well, it turns out there is, but that's okay. Let's pretend for a minute just for our discussion here. There is no corresponding real value function that behaves like a factorial. Okay, again, it turns out there is. There's a thing called the gamma function, blah, blah, blah. Not the point. But by the normal definition of what you would think of with a factorial, or whatever that was. But there is no corresponding real value function that does that. So you can't use L'Hopital's rule, right? Because what the heck is the derivative of the factorial? It doesn't make any sense. So this one, you have to just think about it. You can play around with the numbers to help prove this to you, but to really see why that is the way it is, wait. You'll see it later when we get to some other stuff. But the point here is it does turn out this guy is still going to go, this thing is going to go way faster than exponential, as it turns out, right? I mean, one thing, that might help to see that, like, let's make this easier. Like, let's look at 2 to the n over n factorial. Think about, like, when n is 10. Okay, when n is 10, what are we talking about? We're talking about 2 times 2 times 1, 2, 3, 4, 5. Oh my god, I cannot count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, but on the bottom, this is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? I mean, yes, you're using a bunch of 2's that are multiplying, but the thing that you're multiplying is constantly going to be the same thing, right? There's going to be a bunch of them. There's going to be 10 of them, right? So there's a lot of things you're multiplying, but the things on the bottom, right? I mean, like these match up, but every single one of these is larger than the corresponding one on the top. So the bottom one is going to be a much larger number, right? I mean, even if I had something like, imagine like, I don't know, 50 to the end, and then over n factorial. So on the top, it's going to be 50 times 50, blah, 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 right? Imagine we're plugging in 10, right? So imagine 10 of these. Now on the bottom, 10 times 9 times 8, blah, 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 all the way down to 1. If you're only plugging in 10 of these, the top is going to be way bigger. Yes. But once I get to 50, now things are going to start lining up, right? Or once I get past 50, all of the ones, not all of them, but there's going to be a whole lot of ones on the factors on the bottom that are larger than the individual factors on the top, right? I mean, if I picked anything less than 50, like 49, right, all of these 50s would be larger than all of these numbers. But eventually, once I get past 50, all of these are still going to be 50, but some of these are now going to be larger than 50. So this would indeed take over, right? So that's the short version of it, but basically that's the thing you need to realize is this would still converge because the factorial is ridiculously fast, right? All right, so that's the idea of sequences. And then one thing I do want to warn you about the sequence stuff, though, you really got to grasp this sequence stuff, this idea of a list of numbers and growing fast, how fast does it go? That idea has really got to be kind of solid before we get to the next idea. So let me know if you have any questions about that. All right.